At some point it stopped. Okay, should be live now. Yes. So it should be live and it should be 30 seconds delay. So you should be about to see the blackboard more or less now. Is that good? Okay, good. Okay. So if you're just tuning in, I just recapped what we did last time. Didn't miss anything. So let's just look at the Schrodinger equation for stationary states for potentials of this form. We've done this before, so it will be a quick recap. So we just have E. I just start with the eigenstate equation. Remember, this is not for general state, just for this energy eigenstate. So we replace it here. Okay. So now we're going to leave just the p square on this side. On the other side, then we have E minus V of x. Remember, E is a number, but V of x is an operator. Okay. And now, if this is true, then in particular, if we put a cat x here, this is also true. This is going to be the wave function Schrodinger equation. So then we have these two terms. On the left, we've seen before what this is. So if we have, we've seen before a long time ago that this is just h bar squared x squared. Oops. And on the right, well, x with e is just a position wave function multiplied by e. And then we have this term here. So let's look at this term there. So we have x, v of x, psi. Well, this is x, and now we just replace this with the integral. So this is the integral dx, x prime. Right, I just replaced this operator with what it is. And then we have psi here. So then you end up with dx, dx prime, v of x prime. And then we have this eigenproduct, this inner product, and then we have this inner product. And this we know is the Dirac delta. And this is just a position wave function, right? So then we end up with what I will write here. So on the left, we have minus h bar square 2 mu. Second x derivative of this. And on the right, we have x minus v of x, right? Because the only survivor term here is when x equals x prime, so you get v of small x, and here's the position wave function. And from this term, we also got the position wave function multiplied by e. Right? So that's the Schrodinger equation that we need to solve. Let's just tidy up a bit. So we put minus we just put all the constants on one side. So you see already that in zones where v of x, if this is a constant, then all we have is second derivative equals a constant times the function itself, which already tells you, oh, this is going to be an exponential or a sine or a cosine, this kind of functions, right? Okay. So now we look at very, very simple examples. And today we keep it general. Then on Tuesday next week, we make it a little bit more concrete. If there's questions so far, no. So we're going to look at settings where there's so-called bounded interaction zone. Meaning what? We're going to have some x left, some x right. I'm going to look at zones where the potential goes like this. It has some value all the way to the left. It has some different value all the way to the right. And then in between, it can be whatever. Okay, so this is what's called interaction zone. So these are very, very simple settings. Right here, for now, we don't worry so much about what's happening there, but we want it constant on both sides. And I mean, this might not always be the most efficient way to solve it, but you could break almost any physical setting where we have a potential depending on position like this. It just make like now, if it becomes strange again, you make another interaction zone and then another interaction zone and so on. So we just break this like this. So p of x is going to be constant VL for x smaller than x left, V right for x larger than x right, and whatever. We will see specific examples of whatever later on. In the middle. And now I'll tell you what the general procedure is to solve this kind of things. So first, we find solutions for the easy regions, right? Then that differential equation is going to be very easy when VL is just a constant. So the recipe is one. Then we're going to glue together the solution. So say we have some solution of the differential equation here, another one from there. We're going to some conditions to, I'll explain this in a bit. And then we're still going to end up with possibly many solutions, but some of them are going to be unphysical, and we rule them out. Meaning, oh, mathematically, it's a solution for this differential equation, but physically, we could never prepare a particle in this state because it will be unbounded, or it will diverge, or other reasons that we'll see. Yeah. So, rule out Good. So we will start here with number 2. So let's just look at what continuity conditions we want to ask of the wave function. Okay. So number 1 is that the wave function is continuous, and we'll talk more about this next week. But one way to look at it is to see that the wave function tells us the probability of finding the particle in some region, and we want this probability to behave like a nice probability distribution, like a nice probability density. So more specific. So if I look, what's the probability of finding the particle in some interval from x1 to x2 for some psi to psi? Well, it's just this from 0 to x1, the x of x squared. And I want this to behave like a probability density. So if I make this interval very, very small, still want it to be continuous in general. So we ask this. I don't ask you to buy this justification right away. I'll try to find a nice example for the exercise class for next week to see what happens if it's not. That's number 1. Number 2 is that the first derivative in order to x for, sorry. So this was general for any wave function, and now it's just for the eigenstates, for the stationary states. So this is continuous if v of x is finite. And so let's just prove this. So note that in particular for the particle in the box that we did last time, this derivative does not need to be continuous at the edges of the box because the potential is infinite. So let's just see. So far, no questions? Okay. So why is that? So we have the Schrodinger equation, right? Which I erased. So let's write it again. The second derivative of this is, sorry. So from here, if you know the second derivative, if you integrate it once, you get the first derivative, right? So this means ddx. This is the thing that we're trying to prove it's continuous. It's what's going to be a constant, which could be VE at some point x0, plus the integral of what's there from x0 to x. Let's put minus because of the thing, of 2 mu p of x. Right. And now, if this thing is continuous, this function is continuous, missing a dx. if this thing is continuous and this thing is finite, so this is a real number, then the whole thing is going to be continuous. If this was infinite, then who's to say what happens to this integral, and it could diverge there. So that's the reason. That was number 2. Number 3. Well, the second derivative for energy eigenstate is continuous if E of x is continuous. And this you can tell directly from the equation, from the Schrodinger equation. So here's the thing we want to prove that is continuous. This one is continuous. This is a number. If this is continuous, then the whole thing is going to be continuous, right? So that's the justification for that. We're done. Then we need a bit more, 2 more physical conditions. So this is no longer continuity, but it's in general physical conditions for the wave function. The first one we know is that it's normalized. So in particular, because by normalized, I mean this. The square of the wave function must integrate to 1, which means that you cannot have any divergent solutions. So and we'll see an example later where we'd have something that you just, the wave function just continues to increase for all infinity, then this integral could never be 1, doesn't matter what constants we put there. So this will allow us to rule out some things. And the second one, which is not obvious a priori, is and this is true for any wave function, and in particular for the energy eigenstates, but it's true for any, is that this must be larger than the minimum of the potential over all x. And why is that? So. Well, we just write what this is. So this is psi h psi, which is, you've got these 2 terms, 1/2 mu psi d square psi plus psi of x psi. So this is for any state. Now this thing here is larger than 0. I can write here a reminder why. Remember that this, if we expand the wave function in the momentum basis, then this is just the integral of dp of p squared and then the momentum wave function squared. And this is larger than 0. This is larger than 0. So this whole term is larger than 0. Okay. And this term here, well, this is the integral dx d of x square of the wave function, right? But this is always going to be larger than if we just replace Vx with the minimum of all the potential, right? It's multiplied by a number, this number changes in V, so I can just It says it's larger than if I had V min dx of this. But because the wave function is normalized, this thing here is 1. So that's just V min. So we end up with the average energy of any wave function needs to be larger than V min. Yep. And in particular for energy eigenstates, this means that the energy eigenvalue must be larger than the minimum of the potential over all x. Good. So these are the conditions that we'll use later on. Not so much today, but in the next lecture when we want to glue the solutions for different parts of the different regions in space. And now we still need to do this part, which is find solutions for the easy regions. So that's what we'll do now. And so we have two options. So now I can plot here also my E. This is the energy eigenvalue corresponding to this eigenstate. And for every region, we have two options. Either E is larger than the potential or it's smaller than the potential, like here. Okay. So let's see. In regions of constant Vx, I just call it V0. We have two cases. Case A, two different letters, is that E is larger than V0. So then our Schrodinger equation is what? Well, x squared psi of V minus 2 minus V0 So this whole thing is smaller than 0 in this case. So smaller than 0. So when the second derivative is the function times a constant with a minus sign, then the general solution for this is, so I can even call this, I can call this thing K square. I'll write in a moment. The general solution for this kind of equation, what's the thing that when you derive it twice, it gives you the same thing, but with a minus sign and some constant? Well, these are things of the form. Okay, yes. Let's be. Because when you take the first derivative, for example, here, you get the k and the I, and when you take the second one, you get the RI, so you get -1. So this is a general form of solutions, and k is the square root of this thing here, 2 h bar minus V0. So some examples that we already saw of this, although we didn't look at them this way. And of course that now these constants depend on the setting. Okay, but some examples we saw. The first one was the particle in a box. That we saw that this was a times some sign at x, but this you can see as a, well, you can just expand the sign in ikx, and now here, I think it's a minus, yeah, over 2i, right? That's just the definition of sign in terms of exponential. So you can think of it being the superposition of a wave moving in this direction and the wave moving in that direction, right? So you had your box and you had something like this, and you can think of it as a wave moving this way and the wave moving that way meet, and the result is a sine function. The other example was a free particle. So for example, moving to the right, then we looked at things like P of x being e to ikx. Remember this plane, this wave's moving that way. The problem is if I just leave it like this, then it's not normalizable. So it turns out that in this case, the eigenstates of the Hamiltonian, you cannot normalize them. Doesn't matter what constant we put here. That's why then we put an envelope, right? That made it look like this, moving that way. Okay. So these two examples of waves that we've seen so far, you can see them as special cases of this. Yeah. Yes.
Can you get the square for the h bar?
Yes, I forgot the square. Yes. So now we have one more case. Which is if the energy is less than the potential in this region. Of course, it cannot be less than the potential in every region, but for a given region, it could be lower. So that's case B, which is E, then V0. So then you get that the square of equals 2 h square V0 I call it. And now this thing here is larger than 0. And I call it B. I call this B squared, larger than 0. So now we have the second derivative of the function is the function times a constant. And the general solutions for this is the sine or the cosine. So then we have, I'll give the constants different names. So C, let me see what I had. Sorry, the sine or the cosine, but there's a nicer way to put it, which is like this. The x was the E. So this is a general solution. With B is again the square root of this thing here, 2 over h bar squared. right? And you can derive this twice. From the first time you get the B, then you get the B again. So you get that. Good. Again, these constants depend on the setting. So let's look at some settings. And you tell me when I should let you out. Like 10 to, let's say. Maybe we do one setting now. So now these are examples of those things. Yeah? So the first example is when E is smaller than the VL or the VR. Okay. Let's do here. L, it's R. This is my initial energy of, sorry, this is the energy of my eigenstate, of my stationary state, and the potential goes like, well, maybe it's here, the L, the R, both are larger than E, and the interaction zone, well, we know that it must at some point come lower than the energy because of this condition we saw before, right? That E must be larger than the minimum of this. So maybe spend some time here, does whatever, comes back up. So then we are in this setting, meaning that we have two possible solutions for both sides. So let's look at the right. Well, we have one BR coefficient that comes from VR here. And then we get two solutions, this and that, and they look like this more or less. So if now I'm drawing kind of the wave function on top of this map. So this is C to the E BRX. And you can already see what the problem is with this one is that it will go to infinity. So when you do the integral, this is definitely diverging, right? This diverges. So then we say, well, this is not a physical solution for the wave function in this region. And this is something physicists do a lot. So they solve the maths and then they see from all the possible solutions, which ones can correspond to actual physical particles. And then you can have another one. This was the other term of the solution, E minus BRX. Well, this one goes nicely to 0, so you can choose this constant such that the whole thing will give a finite integral, so that's good. So we keep it. And on the left, we have the same thing. So we have sorry, this one is C. Ah, no, this would be D prime. In the lecture notes, the conclusion is right, but there's a confusion of symbols from here to there. But anyway, this is E minus BLX. Right, because it diverges, it decreases with X. And again, this diverges because if you go to minus infinity, this thing is huge. So we discard this one. And something like this. So this would be C prime BLX. This converges, so we keep it. So then what are the solutions here? Set tag 0 of X is going to be D, sorry, not D, no, C. Oh, C or C prime, whatever you want to call it. E to BRX for X more of XL. D. Yeah, actually, there's a typo in this note. X started of XL. And something that we don't know yet because it depends on the form of the interaction zone in the middle. Yeah.
Shouldn't the B from the C to B prime be BL? Or was it?
BL, yes, sorry, yeah. Exactly, yes. So what's an example? So let me just type what it looks like. So it looks like, so this is kind of E of X, it looks like this, yeah. Look, then it can be something, we don't know, and then it goes down again. Okay. Where this is, these are the XL and X, right? So what are real life examples of this? In the lab, for example, when people want to make quantum computers, they want to have some particles that are super well localized in a small region. So for example, in trapped ion computers, you have like a series of atoms. They're not atoms because you remove or add some electrons so that they're ions, just because then they respond to an electric field. But you want them to be very confined in some region because then you want to shoot lasers at them and hopefully hit just one ion to apply your like qubit rotations and so on. Right? So what they do is to use a V of X that is, in fact, I think it's just electric potential to confine this to this region, which means that this ion's wave function will decay very rapidly outside the region, which means like if you were to measure it, for example, by shooting an atom, a laser at it, we're very likely to find it in this region. Okay. This is also used, I mean, this is just one example. It's used in all sorts of labs. Okay. Is it time to end? When did I start?
You need to do some more.
I don't care. So I think I will, no, I don't care. I will do the next in the rest. So we saw this example and now we still need to see the two other examples of when they're both lower than the energy and when one is lower and the other one is higher. Okay? But I think it's better if we see them all then next week and then we recap there. Okay, so we finished today. Have a good lunch. See you on Tuesday. As I said, I will upload, I think I'll upload one of these cases because now we're going to look at 3 or 4 different kinds of interaction zones and the procedure is almost all the same. So one of them I'll just record it and upload it. Yeah.
Is it possible that minus here?
No, because I swapped them.
Oh, I did.
Right? That's, yeah. Yeah.